Hello, this is my first time doing this, so be patient with me. We are getting ready to start Chapter 4, which is Aqueous Reactions and Solution Stoichiometry. So first we need to define what a solution is. A solution is simply a homogeneous mixture of, that was my son, a homogeneous mixture of two or more pure substances. There's two parts to a solution. There's the solvent, which is present in the greatest amount, and for our purposes, the solvent is going to be water, since we are talking about aqueous solutions. Technically, though, the solvent could be alcohol, gasoline, or any number of things. The thing that gets dissolved in the solvent is called a solute. Hold on, we have a...
What about kittens?
I pause this. Alright, the solvent is the substance present in the greatest abundance or the greatest amount, which will be water for us. And the solute is the substance that is being dissolved in the solvent, like salt or sugar. Alright, so for us, as we're talking about aqueous solutions, or aqueous solutions, however you wish to say it, that indicates that the solvent is water. The solute can be an ionic compound like salt, it can be an acid like hydrochloric, it can be a base like sodium hydroxide, or it can even be a molecular compound like ammonia, NH3, or CO2. Alright, the fancy word for dissolves is dissociation. When an ionic substance dissolves, it's called dissociated. What that means is the ions in the ionic compound disassociate. They separate from one another. The solvent actually pulls the individual ions from the crystal and solvates them. So what this is a picture of, the green and white, is a sodium chloride salt. Okay, we've got our little positive sodiums and our little negative chlorines, and they're all stuck together fairly nicely as an ionic salt crystal. But then when you plop this crystal into a bunch of water, all these little Mickey Mouse ear looking water molecules basically attack it and tear it apart. All the little white positive hydrogens, partially positive hydrogens, pull on the negative chlorines, and then all the partially negative O's pull on the positive sodiums until all these ions are separated from each other and the crystal is dissolved. So that is dissociation. Now, when a substance dissociates into ions in water, it can conduct electricity, so it is called an electrolyte. A non-electrolyte is a substance that dissolves in water, but it does not dissociate or break apart into ions when it dissolves, so that's a non-electrolyte. So an electrolyte is simply a substance that, once it's dissolved in water, the solution can conduct electricity, hence the word electrolyte. A non-electrolyte is a substance, when you dissolve it in the water, does not conduct electricity. So here's some examples. Over here on the right, we have a strong electrolyte, like salt water or hydrochloric acid. Those are strong electrolytes because they completely dissolve and dissociate in water, so there's a lot of ions floating around, a lot for electricity to flow through, so we can get our light bulb to light up. Now, on the opposite end of the spectrum, we have non-electrolyte substance that, when they dissolve in water, do not produce any ions at all, and so the light bulb doesn't light up. But there's also some gray area in the middle. There are weak electrolytes, like a weak acid, like acetic acid, or a weak base, like ammonium hydroxide. Those will dissolve in the water, but they don't completely dissociate. Not all the crystals, not all the formula units will separate in the water, so it'll only conduct electricity weakly. So it's a weak electrolyte. Now, pure water by itself is a non-electrolyte. I know we say to get out of the swimming pool when there's a thunderstorm in the area, whenever we see lightning or anything. That's because pool water, lake water, whatever, is not pure water. Even in your bathtub, that's not pure water. There's ions floating around in it, so it will conduct electricity. But pure, just H2O, does not conduct. Now, substances that dissolve in water but don't produce ions are called non-electrolytes, so the light bulb won't light up at all. So basically, we're going to talk about dissolving 4 different types of compounds in water in this unit on aqueous solutions. So first off, we'll have molecular compounds or covalent compounds. They're just made up of 2 or more nonmetals that can dissolve in water, like CO2. You can see how soda is carbonated. That's called a molecular compound, or I frequently say covalent compound if it's just nonmetals. Now, when those dissolve in water, they don't produce ions, so they're non-electrolytes. Now, we've also got ionic compounds made up of a positive and a negative ion. Generally, your positive ion is a metal and your negative ion is a nonmetal or a polyatomic ion like sulfate or nitrate. Then we've got bases. Those involve a positive ion like sodium and the hydroxide ion, OH negative. So sodium hydroxide is a base, as you already know. And then our aqueous acids are simply compounds that contain H plus and some kind of negative ion that's usually a nonmetal like Cl, so HCl, hydrochloric acid. So those are the 4 types of substances we're going to talk about dissolving in water. Covalent, molecular, ionic, and then acids and bases. All right, now, while all these substances can dissolve in water, they don't all do the same thing, actually, on a molecular level. Your ionic compounds like NaCl, and basic compounds like sodium hydroxide, and your acids like hydrochloric do all dissolve to produce ions in water. But molecular compounds like ICl, iodine monochloride, the solid will disappear, it will dissolve in water, but no ions are produced, so those are non-electrolytes. The first 3 are electrolytes, this last guy wouldn't be. Alright, so here's a little chart that's helpful to keep track of who is an electrolyte and who isn't an electrolyte. Okay, soluble ionic compounds tend to be electrolytes. You know it's ionic if it's got a metal and a nonmetal. How do you know if it's soluble? Well, there's a list of solubility rules, and you just have to commit those to memory. Now, molecular compounds, on the other hand, tend to not be electrolytes. Okay? The exceptions to that would be acids and bases. So, molecular compounds are usually non-electrolytes unless they're acids and bases. Okay, it can be strong or weak. Well, how do you know a strong acid from a weak acid? Well, we know acids start with H, but which ones are strong? Well, there's a table, table 4.2 lists the 7 strong acids. Once again, you just have to commit that to memory. So if it starts with H and isn't one of those famous 7 strong acids, then it must be a weak acid. Now, there's only a few weak bases we'll talk about. The only one I'm going to mention right now is ammonia, and H3 does dissolve in water to produce ammonium hydroxide, NH4OH. That does dissolve, what's the word I'm looking for? It does dissolve slightly in water and dissociate slightly in water and produce some ions. So it is a weak base, but it doesn't disassociate completely. So, molecular compounds, stuff made out of just nonmetals, those are non-electrolytes unless it's some kind of acid or a base. Alright, so here it is again. A strong electrolyte disassociates completely when dissolved in water. The strong electrolytes are going to include anything ionic that's soluble and your 7 strong acids. Now, your weak electrolytes, they only partially disassociate in water. So they're only going to conduct electricity a little bit. Those are your weak base, ammonium, NH4OH, ammonium hydroxide, and any acid besides your 7 strong ones are going to be weak acids, weak electrolytes. All right, so here are the 7 strong acids, HCl, HBr, and HI. Now, you might notice HF is missing. HF is not a strong acid because it doesn't completely disassociate in water. Now, it's a very, terrible acid to get on you because it reacts violently with your bones, but it does not completely disassociate in water, so it is not considered a strong acid. So we've got our halogen acids except for HF, that's weak. And then these guys, hydrochloric and perchloric, those are strong acids. Nitric and sulfuric, those are also strong acids. Now, your strong bases I didn't really list any strong bases before because those are kind of taken care of with our solubility rules. You don't have to memorize your strong bases. It's simply any hydroxide that's soluble. So that is part of the solubility rules. So anytime you have a hydroxide with a group 1 metal on the front of it, like lithium hydroxide, sodium hydroxide, that's a strong electrolyte. If it's soluble, if it's a soluble hydroxide, it's a strong base. Now, the other soluble hydroxides are the ones in the bottom of group 2, calcium, strontium, and barium. So all group 1 hydroxides and the bottom of group 2 hydroxides are strong bases. All right, now here's the solubility rules I mentioned before. These tell us what will dissolve in water. And also, there's our strong base rule right there. So the first rule isn't really on here. It's just one of the first ones I think is helpful to memorize. If it's got a group 1 metal at the front of it, sodium, lithium, potassium, it will dissolve in water. Now, there's the ammonium ion, NH4+. He's +1, just like the group 1 metals, and he behaves chemically just like an alkali metal, just like a group 1 metal. So anytime you see ammonium or group 1, that is going to dissolve for sure. Okay, it is soluble. All right, so going through the rules, we've got all the group 1 and ammonium are soluble. All nitrates are soluble without exception. All acetates are soluble without exception. Now, your fluorine compounds tend to not be that soluble, but the other halogens are. Cl, Br, and I are all soluble with 3 exceptions. Silver, mercury, and lead. So like silver chloride, mercury bromide, lead iodide. Those would not dissolve in water. Those would be what we call a precipitate. They won't dissolve. Now, sulfates tend to be soluble except for strontium and barium, mercury, and lead. Those are insoluble exceptions. All right, now these ions down here, they tend to always be insoluble with a few exceptions. And one of those exceptions is always going to be the group 1 rule. If there's a group 1 rule with them, they are going to dissolve. So sulfide compounds tend to not be soluble, except when there's ammonium or group 1 and the bottom of group 2 with them. Then they will dissolve. Let's jump down to hydroxide since he follows the same rules. Hydroxide compounds tend to not be soluble. They don't want to dissolve in water unless they're with a group 1 metal or ammonium or the bottom of group 2, calcium, strontium, and barium. Now, carbonate and phosphate follow the same pattern. They are insoluble with the exception of when they're with ammonium or any group 1 metal. Okay, that's the only exceptions, the group 1 rule. Okay, if there's a group 1 metal in it, it's soluble, and all nitrates are soluble. Those 2 rules, if there's a group 1 metal in it, or if there's a nitrate in it, it's soluble, that will take care of you like 90% of the times in terms of solubility rules. You'll see what I mean when we get into some problems. All right, now, here's another summary. Strong, weak, and non-electrolytes. Your strong electrolytes are your strong acids. Those 7 you have to memorize. Your strong bases are your soluble hydroxides. So any hydroxide with a group 1 metal or the bottom of group 2, calcium, strontium, and barium. Those are strong electrolytes because they are soluble, completely soluble in water. And then any other ionic compound that is soluble in water is also a strong electrolyte. So sodium chloride would be an example. Now, your weak electrolytes include your weak acids. Those are any acid, something that starts with H, that is not one of the 7 strong acids. Those are going to be your weak acids. The only weak base I want you to worry about right now is ammonium hydroxide. Now, what's your non-electrolytes? Anytime you dissolve a molecular compound in water, like sugar, okay, that's not going to have ions in the solution, so it's a non-electrolyte. All right, so electrolytic solutions contain these mobile positive and negative ions, cations and ions floating around in them, and that's how the electricity is conducted. So your ionic compounds, your acids, your bases, they produce ions when they are dissolved in water. Now, we're going to write out these equations called dissociation equations that just show what a compound